In this video, we are going to solve a ratio problem involving a gravitational fields. Here's the scenario. We have two planets, A and B. Planet A has a mass of m and a radius of r. And planet B is a bit different. It has half the mass, but double the radius. Our goal is to figure out how the gravitational field at the surface of planet B compared to the planet A. To make this easy, let's follow the same simple step-by-step process we used previously for ratio problems. You can also click the link above to watch a video on a different ratio problem if you need a refresher. The first step is to identify your variable and the key equation for that variable. In this case, we are looking for a gravitational field G. The formula or the key equation we need is the universal law for G, which is the capital letter G multiplied by m, then divided by r squared. So in this equation, the capital letter G is the universal gravitational constant, and m represents the mass of the planet. R is the distance from the center to the point where you are measuring the G. Since we are looking for the field at the surface, r is effectively the distance from the core, or the center of the planet, to the surface, which is just the planet's radius, right? And this formula is really the engine behind everything we are going to calculate. The second step is to list the variables for each situation. And let's keep our data organized. For planet A, the mass ma is just m, and the radius ra is r. For planet B, the mass mb is m over 2, and the radius rb is double the radius, which is 2r. Since the capital letter G is just a constant, it stays the same for both, so we don't need to worry about it changing, and let's leave it alone. And the steps 3 is substitute and compare. Now let's plug those values into our equation. For planet A, we simply apply these specific parameters to our general formula, so we get Ga equals the capital letter G multiplied by ma divided by ra squared, which equals to G ma is m and ra is r. So we get gm over r squared. Even though this formula looks almost identical to the general equation, it is important to define it clearly as our specific expression for the planet A, so we'll have a solid point of comparison. For planet B, we have to be careful with the math. So GB is G multiplied by its mass mb over rb squared. Then it equals to G multiplied by mb is m over 2, and then divided by rb is 2r, then squared. This expression can be expressed as gm over 8 multiplied by r squared. I've broken step 2 and 3 down here to keep everything crystal clear. However, once you get hang of it, you can speed things up by jumping straight into writing your GA and GB expressions by substituting your variables directly into that key equation. Okay? The last step is just set up and simplify the ratio. When we take GB over GA, we get GB is GM over 8r squared, then divided by GM over r squared. All the common terms, the G, M, and r squared, all cancel out. Okay, eventually this gives us 1 over 8. And this leaves us with a very clean relationship. And then we can rewrite this to show the final answer, which is GB equals 1 over 8 of GA. And there you have it. By doubling the radius and having the mass, planet B's gravitational field ends up being exactly 1/8 that of planet A.